All right, last time we started section 3.5, we were talking about multiplication and division algorithms, and we haven't gotten to the division part yet. But that's where we're going to pick up. We had done some different exponent properties because that's related to multiplication, and then also some multiplication algorithms. And now we're going to take a look at division algorithms. So the first division algorithm that we're going to talk about is the standard algorithm. There aren't as many division algorithms, by the way, as there are some of the other ones. So the standard algorithm for division, this sort of sounds like a funny thing to say, but I'm going to say it anyway, relies on the fact that you know the multiplication table for whatever you're dividing by. So if you're dividing by single digits, for the most part, most kids are pretty okay with that. Because you know most of the time, unless there's a special circumstance or something surrounding it, you learn your multiplication tables for 1 through 10 or 1 through 12, okay? So as long as you're dividing by one of those numbers, the standard algorithm is pretty fluid and works pretty well. If you've got a special needs situation, students who have difficulty with memorization and stuff like that, you've got other issues at play. But let's go through the standard algorithm, and I'm going to use the language that I use when I think it to myself. Maybe your language sounds a little bit different in your head, but I say something like this: how many times will 5 go into 6? Because 6 is the first number, and the answer would be 1. And so we write down the 1, and then we multiply. 1 times 5 is 5, and then we subtract. So 6 minus 5 is 1. And then we bring this down. Maybe you draw an arrow, maybe you don't. It just depends on kind of what you're used to. And we have now the number 12. So how many times will 5 go into 12? Twice. And again, you know this because you know your multiplication tables by 5s. That's why you're knowing this. 2 times 5 would be 10, and we subtract to get 2. And then again, either draw the arrow or don't. Your 3 comes down either way. And we say, how many times does 5 go into 23? And the answer is 4. 4 times 5 is actually 20. And then when you're first learning division, what do you do with the 3? Do you remember? We write a remainder, and so that's where we're going to stop on our division process here. So we have 124 remainder 3. Now, like I said, that works great when you're dividing by a single digit number, pretty much. If you were dividing by 35 or 37, that process doesn't work as smoothly, and sometimes you guess wrong. Sometimes you say, well, I think it goes in 4 times, and you find out, nope, it went in 5 times, or nope, it went in 3 times, and you have to erase and you have to rework. Do you guys know what I'm talking about? Okay. And again, for the children, and there are children who have legitimate special needs with mathematics, and the memorization thing just doesn't work very well, this process is just as difficult as if you were dividing by 37, because those facts are not quite, memorized the same way. So let me show you the repeated subtraction algorithm. Now, the benefit is that you don't need to know your multiplication tables, okay? So special needs situations or dividing by a number that's larger or something like that, that's great. The detriment is that sometimes this can take many steps. It's not terribly efficient. Now, I hope that by now you realize that there's always a pro and a con when we're doing different methods, including the ones that you know and love. So that's the con here, all right? So let me show you how this works. We take the 623, and we are going to repeatedly subtract the number 5. But obviously, we don't want to subtract 5, because that would take forever. Right? It would actually take us 124 times. So that's not what we're doing. We're doing a modification for that. What we do is we subtract a 5 followed by zeros wherever possible. So I can actually subtract 500 from this. That's possible. And I get 123. And what I actually did to get 500 is I did 5 times 100. So out to the side of this, I'm going to write down 5 times 100 because it's going to be easier to find out my answer if I've written those to the side. Sometimes I don't have people write down 5 times 100. They just write down 100, that they multiplied by 100. That's fine. Now, I can't subtract 500 anymore. Why not? Yeah, it would be negative. It's too big, right? But I can subtract a 5 followed by a 0, namely the number 50. So what would 123 minus 50 be? $73, yeah. And out to the side, I'm going to write down that this is 5 times 10, or you could just write times 10. Can I subtract another 50? Yeah, I can. So I will do it again. So I'm going to subtract the 50 as many times as possible until the number gets too small. So 73 minus 50 would be 23. And again, out to the side, I'm going to write that this is 5 times 10. Can I subtract another 50? No. So I started with 500, and then I did 50. What do you think I'm doing next? 5. That's the last thing I can do in this particular problem. So 23 minus 5 would be 18. And to the side, I'm going to write 5 times 1. Or again, you can just write a 1 if you would like. I can subtract a 5 again to give me 13. Again, that's 5 times 1. Let me move up here. From the 13, I can subtract another 5, which would be 8, which is 5 times 1, right? I can subtract another 5 to give me 3, which was 5 times 1. Can I subtract another 5? No, I'm done. Okay, so I'm done when the number gets too small, basically. Now, how do I find out what answer I have? What is my answer? Well, you might recognize the 3 at the end. The 3 at the end is the remainder, right? That's what's left over, just like the 3 over here was left over, right? The answer is actually the numbers you multiplied by. That was supposed to be a highlighter. 100, 10, 10, 1, 1, 1, 1. What if you add all those up? Yeah, you get 124, don't you? So we have 124, and then at the end, we've got the remainder 3. And a couple things just going to throw out there because I always have people try to do other stuff on this one. You can only multiply by powers of 10. Okay? We're in base 10. That's the numbers 1, 10, 100, 1,000, 10,000. So you can't do 5 times 4 at the end and just say, oh, 5 times 4 is 20, so I'm just going to multiply that out and subtract 20. No, you're only going to be subtracting 5s and 0s because that's what you're dividing by. So if you were dividing by 37, you would only be subtracting 37, 370, 3,700, and so forth. 37 followed by zeros. Are you with me? And again, the reasoning and the thinking behind that is that there's no need for a multiplication fact if I'm using repeated subtraction. But if you go trying to subtract 5 times 4, that was a multiplication fact that you just used. Does that make sense to everybody? Okay, so as you can see, this could be very tedious if the number had been 959, right? Yeah, because you would have to subtract 900 how many times? I mean, like, whoa. Have to subtract 100 how many times? 9 times, right? That's not especially efficient. It's not really very conducive, but there's a place for it, okay? So I wanted you to see that. All right, the last pieces that we have for today are some combination kind of problems, and then we've got some mental math stuff and estimation stuff going on. So we're going to take a look at these problems from the perspective of using alternate algorithms. I know you know how to multiply and divide with the standard algorithms that you know and love. So our focus is going to be on using the alternate algorithms, especially since it's been, I don't know, 10 days or something like that since I last saw you and we talked about the multiplication algorithms, okay? So here's our first one. Anybody know how to say this guy's name? X. Is it Juan? I keep feeling like it shouldn't be an X if it's Juan, but all right, we're going to go with Juan. Juan saved $5,340 in 3 years. If he saved $95 per month the first year and a fixed amount of per month, during the last 2 years, how much did he save per month during the last 2 years? All right, so we've done problem solving in this class. There's more than one way to solve problems a lot of the times. When you're reading this and you're looking at it, what do you think you might try first? Okay, so why 95 times 12, Brianna?
Because that's what he saved per month in the first year.
Fantastic. So the first year, whoops, I don't think I did that right. There, $95 per month in the first year. That's the piece that we started with, and I agree with you. I think that's a good place to start. Okay, so again, I'm not going to do standard algorithm because I told you that we weren't. So let's do a different one. How about partial products? I'm partial to that one, actually. So we have 90, we have 5, we have 10 and 2 for 12. Okay, so if you'll remember the way this one works, each row and column gives a multiplication fact. So 90 is the first column and 10 is the first row. What's 90 times 10? 900. And then I can do 90 times 2 directly underneath it if I want to. So what's 90 times 2? 180. I have 5 times 10 in the top right box. It's 50. And then 5 times 2 in the bottom box. 10. And we're going to add these facts up. So if I were to add 900, 180, 50, and 10, what would I get? Good. 1,140. All right, what am I going to do with that 1,140 now? Okay, so this is how much he saved during the first year, and what am I going to subtract it from? Right, the 5,340 that he saved over the course of the 3 years. What is this going to give me when I'm done? I don't mean what number, what quantity. What am I finding?
How much he made in the last 2 years.
Right, how much he saved in the last 2 years. Okay, that's what we're going to find. So what is 5,340 minus 1,140? 4,200, good. Okay, now what? You can divide by 24. Is there another way you could do it? I'm just thinking, like, in my mind, 24 is not super easy to divide by because I don't know multiplication tables for 24s.
Divide by 2 and then divide by 12.
Okay, and so why would that actually make sense in terms of the context of the
You're
problem?
doing it per year.
We could think of it per year. Does that make sense? So is it okay to divide by 24? Of course it's okay to divide by 24. But it would also be possible that you decided that you wanted to divide it by 2 and then divide it by 12. And especially those particular numbers are useful because most multiplication tables that kids learn go up to the 12s, these days anyway. So those are actually pretty nice numbers to divide by. So I'm going to go with that one just so that we can do something a little bit different. What would 4,200 divided by 2 be? We'll just do standard algorithm. This one's really nice. 2,100. Everybody good with that? Okay, 2,100. It's nice and even. It's really very nice value. And then just so that we have a chance to practice with the repeated subtraction, even though I said that this would allow us to use our multiplication facts, let's practice the repeated subtraction to see how it works with a 2-digit number because our last one that we did was a 1-digit number. So remember, it's always the number that you're dividing by, in this case 12, followed by zeros. So how many zeros can I follow the 12 by and still subtract on this? 2. I can do 1,200. So 1,200 is 12 times 100. So what is 2,100 minus 1,200? It's 900, right? All right, so then can I subtract 1,200 again? No. So what am I going to be able to subtract next? 120. That's right. That's 12 times 10. So what is 900 divided by, or subtracting, 120? 780. Good. Can I subtract 1,200 or 120 again? Yes, I can. Okay, so I want you guys to go ahead and fill this in, as I am too. Keep subtracting 120s until it gets too small. This is that not terribly efficient process, right? Because there's quite a few you have to subtract. '80 is where I ended up. Did everybody end up at 80? Yeah? Okay, I can't subtract 120s anymore, but what could I subtract? Uh-huh.
On your 660, it was 5. It's 5.
Ah! Thank you. I knew when I was moving quickly through there I was going to make a mistake. 5, 4. So do we get to 60 as our final one? Thanks. All right, good deal. Okay, now what can I subtract from my 60? Thank you. 12 is right, yeah. That's 12 times 1. What's 60 minus 12? 48. Now you guys have to double check my subtraction. 36. Okay, I got to 0. Did everybody get to 0? Oh, good deal. How many subtractions did we do? Well, there's 100. Whoops. There's 100. And then I have 10, 20, 30, 40, 50, 60, 70. So that's 170. And then I had 1, 2, 3, 4, 5. So it's 175. A question asked us, how much did he save per month during the last 2 years? So this is 175 what? Dollars, exactly. Now, when you're doing problems, and you'll have a few of them like these in your homework, you don't have to use all the other algorithms. It's okay if you don't. So unless something specifically tells you you have to use repeated subtraction, you don't have to use repeated subtraction, and it's okay if you choose not to. I would encourage you to try some of the different algorithms when given the option, just so that you can be more comfortable with them, because when you do get to a test, there will be places where I will say you do need to use repeated subtraction, and so if you've sort of shortcutted yourself a whole bunch of times and you don't remember how to do it, then that's going to be unfortunate, okay? All right, let's try another one. Dan has 4,520 pennies in 3 boxes. He says there are 3 times as many pennies in the first box as the third, and there are twice as many in the second as the first. How much money does he have in each box? I know you really just want to take it to a coin counter, right? The thing you dump it into and let it count it. So what would you do in this situation maybe to start as you're thinking about this problem? I'm tempted to draw 3 boxes. How about you? Can we do that? So we have 3 boxes. And tell me what information you know about these 3 boxes. What's it say? 3 times as many pennies in the first box as the third box. How many are in the third box? We don't know. I mean, right? Yeah, we don't know. So we're just going to call it X or whatever variable you like. P if you want to for pennies, it doesn't matter. But there's a certain number of them. We just don't know how many there are. But once I can put something in that box, then what should I be able to do for box 1? I can write 3x because there's 3 times as many. How about box 2? What does it say about box 2? Twice as many as box 1. What would that look like? 6x, right? 6x is twice as many as 3x. All right, this is a good place to start. Now it says, how much money does he have in each box? So what do we know about all these boxes? Total. They're equal to the total number of pennies, right? So how many x's do I have here? 10. There are 10 x's if I add these boxes together. Maybe I'll just do that just for sake of saying that we did. 3x plus 6x plus x, all my 3 boxes, equal the 4520. And that's 10x equals 4520. Whoops, left the 2 out. There we go. So what would I do then to find out how many or what value x holds? I divide by 10, right? So if you want to think about it from the perspective of like a non-algebraic standpoint, right, we're dividing by 10. You could do it long division style. It's easier to do it fractional style, right, because there's zeros on the ends of both of them. But this goes in 452 times. If you think about it like this, of course this only works because it's a 10. The 10 divides with the 0 on the end. So x is 452. Now, did we answer the question that was asked? Not quite. What question was asked? How many are in each box? In fact, not exactly. It asked how much money is in each box, right? So x being 452, what does that tell us? Right, it tells us that box 3 has $4.52. What would I have to do to find the other two boxes now? Multiply them. Okay, so box 1 maybe. We go to box 1. What would we do to find out how much money is in box 1? We would multiply that by 3, right? So what is 452 times 3? Well, we can write it out with any of the methods of algorithms we've done. For the sake of what we're doing right now, I'm going to have you just go ahead and tell me the answer so we can move on. What would 452 times 3 be?
1,356.
Right, and if we do it in money, it would be $13.56. I should say in dollars, if we do it in dollars. $13.56. And what would I do to find box 2? I would double the $13.56, right? So what would that give me?
2,700.
Right, $27.12 after you turn it into dollars. All right, a couple of interesting pieces that I want us to take a look at about a student. A student observes that 39 plus 41 is equal to 40 plus 40. And that's true, right? Okay, good. And they ask if 39 times 41 is equal to 40 times 40. How would you respond? We talked about this a little bit during your questions at the beginning, right, from 3.4. And I mentioned that the first thing you should do is to try and figure out what? If it's true or not. Does it work? So how could I find out if 39 times 41 is equal to 40 times 40? Multiply that, right? Absolutely. So grab a calculator for us. What is 39 times 41? Oops, there's a 1 missing. There we go. 1,000, what was it? Yeah, 599. And what is 40 times 40? 1,600. 1,600. So the answer is they're not equal, right? They're close though, correct? So like if you were wanting an estimation, would this be a pretty good way to estimate? Absolutely, it'd be great. A great way to estimate, but they're not exactly the same. So we would say something like that. Anytime a question asks you, how would you respond or explain, it means with words. Like you're talking with somebody because you're a teacher, right? Or you're tutoring or whatever. You have to use language to do that. So the answer is no, they're not equal. And if you want to add, but they're close or they're approximately the same, that's a great thing to add. So now we have another student who's going to take it like one step further. Another student observes that 39 times 41 is equal to 40 times 40 minus 1. They're only 1 apart. He also finds out that 49 times 51 is 50 times 50 minus 1. Again, they're only 1 apart. And he wants to know if that pattern continues. Will it always work? That's what he's asking. And if it does, what relationship has to happen between the first and the second values in the equation to make it work? So what does this relationship currently look like that he's trying to establish? It looks like there's a possibility, maybe they're 2 apart. What's another possibility? There may be a possibility that there's an issue of them being odd, or maybe even that they're surrounding the number 0 where there's a 0 on the end. Do you guys see that? I mean, those are all possibilities there. That's what his second part of his question is sort of like leaning towards is, okay, but when would that actually work kind of thing? So I actually want to show you how you can think about this from an algebra standpoint. So this isn't what you would show the child. Please don't misunderstand my working out this particular problem this way. But this is something that you guys have the ability to think through given the mathematical backgrounds that you've had. It looks like at the very least the numbers are 2 apart, right? That was the first thing. I think Brianna said it, that they're 2 apart, and they definitely look like that they're 2 apart. So I'm first going to take 2 numbers that are 2 apart that I don't know what they are, and the easiest way to do that is to do x and x plus 2. Does that make sense to everybody? Yeah. Okay, so there's 2 numbers that we don't really know what the x has to be to make that work, but we're trying to figure that out. Now, if I were to multiply this out, like distribute, what would I get? X squared plus 2x. Okay, so we're going to pause on that for a second. Take a look at the right-hand side of his 2 equations now. What does he do to the 39 and the 41? How are the numbers 40 and 50 related to the first 2 numbers that he started with? He what? He rounded them. You could think of it that way. It's in the middle. You might say it's like halfway. And given the numbers that he started with, if I had called mine x and x plus 2, what would that number be? It'd be x plus 1. Because x plus 1 is halfway between x plus 2 and x. And he multiplied it by itself twice, correct? So pause with me and consider to distribute or FOIL or multiply out, whatever language it is that you have most recently heard used. What is x plus 1 times x plus 1? And remember, you do have to multiply all 4 pieces, right? It's a 4-piece thing here. So if you start with the first terms, that's x squared, right? Good. X squared plus 1x plus 1x plus 1. And if I combine the like terms together, these two, 1x and 1x is 2x plus 1. I'd like for you to compare these 2 quantities. How are they different? The plus 1 on the end. That's the only difference, right? The second one is exactly 1 more. So if I took away that 1 more, namely this minus 1 right here that he's doing, if I take away that 1 more, they're going to be the same. And it didn't have anything special to do with it being surrounding 0, or something like that. The 2 apart was enough. So that suggestion of it being, or does it work for just numbers that are 2 apart? Actually, it does. Now, it wouldn't necessarily be helpful to do 42 times 44 and be like, okay, I'm going to do 43 times 43. I mean, why? It's just as hard a problem, right? So there's something nice about the fact that the numbers that he picked are surrounding 0, obviously. It made it easier to do. But there's nothing special about it being the only ones that work. Does that make sense? Okay, so let's kind of write down a little bit of a fact here. So this will always work. When the numbers are 2 apart. All right, so here's what we're gonna do. We don't have time for the mental math part that's coming up next in the estimation. Those parts won't take us very long. I mean, maybe max 10 minutes. So we're going to do them next class period on Wednesday. We'll do this last, basically a page and a half-ish of our packet. And we'll do group work for that as well that day. And so this assignment won't be due until the following Monday, so the Monday after Easter. I would encourage you to start working on it because campus is going to shut down and you're not really going to have an opportunity to ask questions the way you maybe normally would over a weekend. So it'd be really good if on Wednesday when you come, if you're having questions, you have those kind of ready to talk with me about, okay? All right.